fully differential readout circuits. In the previous class, we learned about single-ended and we also learned about inverter-based readout circuits. Now, what is the difference between single-ended and fully differential circuits? The difference is single-ended will have a single input coming into the operational amplifier or any high gain amplifier circuit, whereas in a differential you will have two circuits. You will have a positive terminal and you'll have a negative terminal, or a positive and a negative sequence, the difference of which is passed through the gain, and the common mode of it is attempted to get rejected and remove it to ensure that we have a better signal to noise ratio, or you have better AC gain in your system. Like in the previous circuit, we will now look at what are the various phases that are present. The two phases we have are clock phi 1 and phi 2, which can be seen here, which are controlling the various switches that are present. If you draw a line across midway across the circuit, you will see that each of them is a mirror circuit of each other. In that, the reason is you will have same except in the capacitance and the sensor value. If you look at the inputs, so we will see typically one of the stages will be an active circuit phase, the other one would be a reset phase. Let us identify which is a reset phase among this. So reset phases, all the phases which ensure, or clock phases which ensure that the capacitance get discharged can be called as a reset phase. Now let us do a quick analysis. When clock 1 is on, terminals A plus and A minus get to ground. When phi switch 2 is here, switch is down, it is grounded. So capacitance C1 and C2 will be grounded with one terminal. Likewise, when you do phi 1, you turn on here, it is again grounded. When phi 1 is turned on, there is a pre-charge happening on this circuit, but since phi 2 is closed, there is no pre-charge, so this is empty. When phi 1 gets closed, then the terminal A1 will go to Vout without going through Ci. Likewise, when phi 1 is closed here, terminal A2, A plus, whatever voltage is given, will go to the Vout minus. And phi 1, when it gets closed here, either gets pre-charged or goes to ground. Let us think that this is a ground terminal here on the top and bottom. So Ci will get discharged. So this is more like an integration capacitor. So how is this happening? So right, all these are closed. So now we understood that phi 1 is almost reset, or it is clean up the value on the capacitance. Now let us look what happens when you try in the opposite direction for the charge to happen, where predominantly we will be looking at phi 2. When you look at phi 2, here when phi 2 is closed, this sensor portion is grounded. Here when phi 2 is closed, this section gets recharged to voltage VR. Phi 2 is closed, whatever is the value of the capacitance difference. So this is a capacitance divider, right? Capacitance divider circuit. Or you could see it as you have a circuit on one side connected to the ground, and you have another capacitor here which is connected to the ground. So you can treat this as C0, and this is your CS, and this node is going to the op-amp amplifier, correct? So this is how you can typically visualize that you are grounded capacitances and the other one is turned on. So when phi 2 is turned on, you have the voltage coming from the capacitors outwards, and it is going into the operational amplifier with a finite gain A0. So what is the voltage that is given across the capacitor? The voltage capacitor divider would be, assuming the input is V in or V out, that would be given as Cs by C naught times V is your voltage divider across each plus Cs. So that will be the voltage, that is its, apologies, it will be C naught because it is across Cs. This will be your output voltage, that will be C net A plus or A minus effective voltage across both the sensors. Here Cs would be 1, 2 and C naught would be common across both. So since the sensor value is coming in the denominator, you can check and see that consistency can be maintained. Right? Now what happens once the capacitance value is fed back at A plus and A minus? Once you feed back at A plus and A minus, you are now here. Once it is present here, now it is only a matter of whether you are operating this in your fully differential op amp and whether it is giving integration or it is only an resistive action that is being seen, where it is only a gain stage or an integrator. In this particular case, we have both reset and integration phases. Reset happens through this phase where A1 directly goes to the switch out into the Vout, and when it is needs to be integrated, it gets integrated over the charge Ci and then it is read out later. So what is the integration value that you get? Whatever is a charge stored at Ci, so the voltage across the capacitor Ci gets to be the voltage across A0 times the gain of the operational amplifier. So A0 times what is the value of C voltage A delta A, or we can call it as this delta A times A0 delta A times A0 will be your voltage Vout plus. So this A0 is directly dependent on the open loop gain. So when you place it in closed loop, this closed loop value reduces and then you process it. So what are the other ways of reading differential? Now what has how this is what it happens in single-ended. In differential, when you're reading both of them, what is the common circuit, right? What is a common noise that is present here, right? Any noise that is present here. This noise comes out as common to both circuits. So these can be effectively nullified with each other. So let us do a quick calculation of what I mean, how it helps in the differential. So if your value at A0, A plus or minus is given as the voltage seen across the capacitors CS2 is effectively CS divided by C naught. So when you are looking at this aspect where the readout circuit is present here, so you know when the capacitors are both in parallel, it is a combination. So you are only looking at one portion of it. So even if it is C naught plus CS2, we will look at CS divided by C naught plus CS times what is the output voltage. So this is your A plus comma minus. So whatever is your input voltage, that value will come. Now, if you have C noise present here, now the C noise also will come in parallel. Now, this C noise definitely gets carried forward to both of them in both sides. Now you have both these two values. To find out the difference between the two, which you want is A plus minus of A minus, you will get a difference by CS1 plus C noise minus CS2 minus C noise divided by sum of all the values C0 plus CS1 plus C noise appears here, and this will be CS1 times or CS2 depending upon that factor value will come effectively. So here the C noise component gets cancelled out and only the difference between the two sensing capacitance values will be there. In this case, C1 is going in one direction and C2 is expected to go into the opposite direction. So the difference will be a large delta C divided by a C common, which can be given here, which is the denominator. So this is effectively the AC component of the capacitor sensor, which gets amplified and brought out. So all our methods in differential is to try and reduce all this common factor, and this common factor effectively becomes a DC component in the voltage. And this DC component in the voltage can be easily nullified or removed by passing through a capacitance, because your DC component in the capacitor doesn't get passes through. So the voltage, common DC voltage or a capacitance, common capacitance values present get translated into a DC voltage, and this DC voltage does not get passed through to the output. You will only be working with the gain or the AC gain circuit coming through. So the delta A that you see here is translated output as A naught times delta A. So this is another way of using a differential circuit to read out a capacitance value.